All right, so go ahead one slide. So as I said before, Stella and Norbert are the architects behind this project. So if there are any extra details, they can basically clarify. The idea is that driven by the trends from the application's needs, so there are, as you may know, several emerging workloads that make better use of accelerators, for example, or even FPGAs. And our traditional workloads, of course, they still benefit from homogeneous CPU configurations at the nodes. So motivated by the workloads, they have proposed a modular system where partitions can be configured in different ways. And this is what they define here as a module. So imagine you have a system where you have several of these modules. Each one of them may have multiple nodes. Most likely they will have tens of nodes, which are self-similar within themselves. But then you may have multiple of these modules. And so what we want to allow in this series of projects is that you can get allocations that are slices of each of these modules. So for example, we do have one simulation code that is weather and forecasting related that makes use of GPUs and CPUs for different parts of its pipeline. So as you may know from weather simulations, you do have, it's essentially a multi-physics setup where you do have certain models for the cloud, certain models for the shore, for the sea, and so on. And depending on the algorithms that are being used, some of them are well posed for GPUs, some of them actually work better in traditional CPU setups. So the idea is for those type of workloads that benefit from different hardware configurations in subsets of themselves. What you can do with a modular supercomputer architecture is to have a reservation for execution where you grab a slice of each type of module and then execute concurrently, instead of how it was done before, where at least in this type of applications we have experience with, the way this was done in the past is if you had a part of the simulation that was GPU friendly, you will run it first, then have all the information in the file system, and then load it to the next part as basically a workflow where the different parts of the workflow were completely separated individual jobs. So in this case, you can instead do partial progress and synchronize over the network and potentially get a huge speed up. But it really depends on the application. If you do have applications that benefit from a single type of node configuration, then of course you would just go ahead and reserve on a single module. But PMIx is very important here because it's what enables the establishment of communication through all these modules, which may have the same type of network communicating them, but there are also some cases where you may have different types of networks, such as InfiniBand and OmniPath, like we had in the past. And so for that, the part of the researchers in the project have done also system software that allows you to match, basically connect MPI across mismatching networks. So you see here, there are two references. We can share the slides later and you can take a look at those papers. So go ahead to the next one, Josh. So as you see here, this was provided by Stella. So this is an example of how could an allocation look like. So in here, the deep learning workflow has a slice of module 5, which is an idea of a quantum computing module, which may come in the future. Also, because you're dealing with large amounts of information, then you can have a slice of a special type of storage that is much faster, but it's a limited resource, so you need to handle it with reservation. And you can combine it with a data analytics module, which is typically a configuration that is dominated by GPU performance instead of CPU performance. So that is a deep that is the data analytics example. There's also a deep learning workflow example. So in that case, it will be basically a slice here called module 4 is called a neuromorphic module. So as you know, there are some experimental hardware platforms that try to mimic the way the brain works, and this can accelerate greatly the deep learning workflows. And then this can be combined with more traditional parts of the systems. It's not the whole workload fits in this experimental hardware. You still need at least a part of the allocation needs to be traditional CPU architectures. So let's go to the next slide. So then to have a rough idea of how this looks like currently, we are working with Slurm. So the way this will look is that the MSA allocation itself is a collection of sub-allocations that are each one of them in modules. So here we are illustrating module A on the left block inside of the MSA allocation block. And then you have module B on the right. So if you look at the blue squares, each one of these represents a node. And what's important to note is that in the left, you do have a certain type of network configuration where you have many CPUs. And then module B's allocation is actually a collection of nodes that may have in the purple block that is a bigger block. This can represent a type of resource that is non-CPU resource. So it could be an accelerator, it could be an FPGA, or it could be even some less common hardware like quantum computing or neuromorphic. So the idea is to have flexible enough system where you can have these slices be composed into larger allocations. And then the role of PMIx is to offer a common interface between the non-local system software. In this case, we are illustrating the Slurm daemons, as you may know, Slurm D, and then the Slurm step D, which are associated with a job step. This communication between the Slurm step D and the application processes, which themselves will be loading a programming model specific library, such as an MPI library, but also it could be CUDA, for example, in module B's case. It could be that some process actually running some CUDA workload and it needs to connect as well to basically the local daemons. So all these interactions, we want to make them have this OpenPMIx as a common interface, common implementation of the PMIx interface, so that all these completely different runtime systems can be set up and they can establish communication among each other. So of course, PMIx is the side of is basically taking care of anything that is the interaction in the node itself. So we still need to do some system software related to establishing the networking. As I mentioned, there's a company that is part of the project that is responsible for this. It's Partech. They do an MPI library that has functionality that can actually mix and match types of different networks. And this enables this communication across not only the nodes themselves having different hardware and different programming models and runtimes, but also that the networks, they can be different. So currently we are working with, this is what I said earlier. So we, in the tools workgroup, we're gonna become much more active once we start working with these intra-node interactions. We are currently developing the synchronization necessary over management networks that needs to happen across these types of modules and nodes. So I'll go to the next slide, please. So then in this slide, we have an overview. This is also thanks to Estela and Norbert that produces common figures. In here, there's the figure on the right is basically an overview of the software stack. So we have at the top, we have the application or workflow, and then they can be implemented using OpenMP, OpenMP ASC, which you may be familiar with. There's also GPI, which is an implementation of Gatsby. that is led by Fraunhofer. And then MPI, we will basically extend with a proposal from the MPI forum, from the sessions group, we would extend existing MPI libraries, so mainly NPICH and OpenMPI, but there's also the Parastation MPI implementation from Parted. So that is those are the interfaces that are available to the user. And then in the middle, of course, then we have the runtimes. So then you have either NPICH or MPI or NPICH or OpenMPI, for example, for MPI. But if you are using GPUs and so on, you may have different runtime systems there. Then the operating system, we don't do any operating system research, so that is not modified in any way. But then we do actually have experimental configurations with hardware that has, I think currently all the hardware that we have has been released, but even pre-release hardware has been taken into account in the prototypes that have been assembled in the past. So then, as you may see, so everything that is an interaction between the runtime system and the daemons that do the distributed memory management is of extreme importance here. So this is really the role of PMIx. It's very important for us to support different programming models. So as you may have seen, sometimes we focus too much on MPI. So in this case, it helps to verify that the interfaces also work well with other programming models. So as I mentioned here, we do have OMPSS, GPI space, and GPI2. Something else that's very important for us, it's actually a big part of the project, is tool support. So we do have the folks from Vampire, they're working on trace analyzers. Also us at TUM, we're working with a memory analyzer, but there are others as well. And we also want to develop monitors. So if you think of trace analyzers, it's very important when you're analyzing the performance of the application that now instead of basically just showing that you have processes, now you may want to show that you do have processes, but they may be running on different configurations or even different runtime systems. So this is quite a bit of work that is necessary, and the folks at Vampire, for example, they are expecting to get a lot of detailed information of how the allocation looks like, which parts belong to which modules, and so on, as input from PMIx, so that they can better present information through the trace visualizer for users. So both collect, analyze, and show this information for the users. So it's not only about the programming models, also the tools need a lot of basically support from PMIx. So the network endpoint setup, as I mentioned, this needs to be, basically it will be a little bit different than the usual use case, because you do have that even the networks may be mismatching. So there's quite a bit of work there. This one is led by Partek, as I mentioned. So then the heterogeneous task mappings, this is something I mentioned. We need to know, as a task, are you running in a GPU node? Are you using all the GPUs? Are you using just one, for example? This type of information we need to make sure that it's exchanged correctly between the runtime systems and the management layer, which is the task of PMIx. So far we are doing integration mainly with Slurm. We are trying to avoid trying to modify Slurm itself. So we're trying to work with plugins. So instead of a single plugin, we're working with a set, because we basically want to increment the use of PMIx within Slurm. And so the MPI type of plugin in Slurm uses a very small subset of functionality that PMIx supports. And so most of other tasks, such as launch operations and other things that PMIx actually supports, and is how Parted is implemented as a reference, this is not used at all in Slurm. So we are trying to change that by extending Slurm via its plugin system. So what this means is that in the end, if we're successful, we're going to have PMIx and have much more coverage of the functionality of Slurm as it currently has. So I actually took a careful look at this. I saw that the use of PMIx in the Slurm plugin is very minimal. It's between 8 operations, perhaps 10 operations, but it's a traditional PMI1 and PMI2 functionality where you just do the process wire up and nothing else. So we will be incrementing this. So go ahead, Josh, the next one. So this is the last slide. So we are entering the second third of the project. So it's a 3-year project, and we are currently a little bit into the second year. So this is why I mentioned that we're going to be very active with the PMIx because it's going to be a big part of the development coming up. So in here you can see the partners. Some of them are from industry, some of them are from universities, as you may know. So thank you for your attention. And if you have any questions, please go ahead now.